Hello, makers, designers, artists, engineers. Thank you for having some more interest to dig deeper into extruded elements. I'd like to show you here how to get to the instructions, specific instructions and generalized instructions on how to use extruded elements and create them on your PC, incorporate them into your personal work, non-commercial work, and maybe make something huge with a very limited 3D printer. So if you go to extrudedelement.com to the workflow page, you'll see a video there for a walkthrough of the workflow, generally how to grab the code, change the code, things like that. You will need a free open source software called OpenSCAD. It's a very simple to use text-based CAD program, and it's simple to use here because you only have to simply copy and paste the text from extrudedelement.com and just follow the instructions. So you copy and paste the library. Here I've got an owl, grabbed that I believe from GrabCAD, and set some element settings. Here there's hexagonal elements with some hooks, and I decided to go with square elements with rounded hooks. And you make sure your extruded element in this OpenSCAD goes taller than your 3D object so that it envelopes it. And then OpenSCAD has a nice function called intersect. And what that does is it simply takes your array of extruded elements and finds where the two geometries, the array of elements and your imported object, finds where they have in common, which means it breaks up your object to make it larger than a 3D printer, or to make a puzzle if you would like to. So then if you would like to go deeper in minute detail about each parameter, go to the About section of extrudedelement.com and down to Software. That's where it tells you exactly getting started here. You download it, just like it said on the workflow. But here it gives you specifically to go to the GitHub repository for the extruded element library. That's simply a text file. I'm not very familiar with GitHub, but I usually just click raw and it opens up this guy. I Control A to select all of it. And then I go over to my, go over to OpenSCAD. And all I do is just Control A and paste it. So there you've successfully imported the extruded element library, and you can start using OpenSCAD. So this is the final window, a spoiler alert, of the video or the walkthrough I wanted to show people on how to actually use it. So the very first frame is how when you paste the extruded element library in, you'll get this 2D tessellation of extruded elements. See, there's no depth to it. It will just have some interlocking elements. And you'll be instructed to then comment out the lines about, here it says 90 lines down. It could be one off or so. Comment that out with 2 backslashes. And if you want to bring them into the third dimension, just uncomment and press F6. F6 is the magic key here. And I'm switching between OpenSCAD instances because recording my screen and generating 3D extruded elements probably will have a fault with the video or the extrusion rendering. So after I press F6 on that, it pops that 2D tessellation or array or patterning of extruded elements into the third dimension. And that was, again, simply by going down to these bubble brackets I have right here are the executed code, where a lot of commenting and uncommenting will happen. And I commented out tessellate, the 2D version, and I uncommented linear extrude, the height of the tessellation. So then the next step, after you like your elements, you can tweak them, you can change them to round hooks. Let's go back to tessellate, because tessellate doesn't eat up too much memory, so let's try to not crash my computer. And so for instance, these are type E. Here all the parameters are at the top. Type E, type of element, is currently at 1 for triangle. I like triangles. let's go down to element fill. E-fill is a nice parameter. So 0 means ligament only. That refers to these long ligaments. If I change that to a filled element and press F6, boom, oh cool, it doesn't take too much time to render the 3D solid. That was an accident, but a cool discovery. So yeah, there's a filled element, and you'll discover through learning on Reddit and from other people exploring, putting a negative in front of E-fill will enable you to punch holes through your extruded elements. Here I've made the holes too large, but yeah, you can play around with the hole sizes so that you have perforated extruded elements. So the next step in the workflow is then to, let's see where we're at on the web page itself. After you've gathered, I might have jumped way ahead, and I do sincerely apologize. So you obtained it, you open the SCAD, and it gives you the 2D image. Press F6 to render your tessellation or your array or tiling of the extruded elements. And pay attention to it'll be a parameter, then what the parameter is called in plain English, and then below that parameter will be all of its possibilities, if they're limited possibilities. Sizes generally aren't limited. You'll just make something too big, and all of a sudden, like I did with that perforations, just blew out the elements, so I needed to shrink down the perforations. Hook types, there are square and rounded hooks. You can see a demonstration of that simply by, let's change that back to E-fill of 1, and let's make the hooks much larger since that's what we're talking about. SH, S usually stands for size. Size a hook to 5, and boom, they're really big hooks now. And now the other type of hook other than that squared hook is the rounded hook. Change that to a 1. And there you go, you got some cool rounded hooks to reduce stress concentrations or play around with being a little fancy. So on to the next portion. After you tweak it and N elements, M elements, that's how wide and tall your array is. You can then adjust the extruded element parameters and extrude that tessellation and get it to where you like it. You can change N elements and M elements, both values to 1, to just have a single extruded element. Go to File and Export, and you can just export and print if you're just interested in a flat sheet of extruded elements for use in 3D printing. Here on to incorporating an object. There's a section called Imported STL Object Options. So if I then go back to the extruded element library and make this a little bigger so I can see all the text. If I just go down to where I see Imported STL Object Options, I might suggest this to you. See how all the comments are gray here and all the parameters are red, the parameter values are red, and the equal signs are yellow? That's really helpful visually. So if you go to Edit down to Preferences, you can change the color scheme if it's a little too overwhelming. Maybe everything's the same color. That would be awful. So change those colors. Anyways, back to the Imported STL Object Options. So in my case, I've been playing around with a Frisbee. I haven't physically made it, but I've saved an STL file I grabbed from GrabCAD, and I simply place it in the same directory where I went to File and Save. Though I should not have clicked File. It looks like it's having a horrible time with that. So anyways, had I not been recording my screen at the same time, it would have imported when I typed in Frisbee, as you can see here in the imported options, frisbee.stl. You then go down to the executed code where you'll be doing a lot of, again, commenting with backslashes, uncommenting, removing those backslashes. And you uncomment this line right here, which is visualize object. It starts with translate, ends with import file name. Meaning this line is importing file name, which frisbee.stl. It is then scaling that imported object by whatever scaling factor you given those options up top. It rotates this. For instance, this frisbee came in sideways, parallel to the XZ plane right here. And so I put a rotation Rx of 90. So it would turn it from here to flat as you see it here in the XY plane instead of the XZ plane. And then the third step it will translate the rotated and scaled frisbee or object, whatever you're working with. So on to the next step on the website. Let's see what that says next. So you've saved it. Observe the orientation and array of extruded elements. By default, the library is set to extrude the array to assemble the array into the XY plane. And the extrusion direction is the Z direction, perpendicular to that plane. So you observe that orientation and how big you've made your array, and then you import your object. As you can see, the frisbee comes in by default perpendicular, XZ plane, and I rotated it using the RX value right here of 90. You can scale your object to, for instance, I wanted here to have a 500 unit diameter frisbee. In OpenSCAD, it's unitless, so 500 units means whatever your slicer, if you're 3D printing, your slicer interprets that as. So 500 units here would mean 500 millimeters. So moving on to importing, rotating, everything's good, scaling, and now you prepare your production preparation. There are values called kerfs, K-E-R-F. I'd like to give credit to a user on Thingiverse. He made PuzzleCutLib. PuzzleCutLib will cut an object and allow it to they have like male and female interlocking members and cut an object so you can print something larger than your 3D printer. So that's another option. Look for PuzzleCutLib on Thingiverse. I ask that you keep all your creations using Extruded Elements off of Thingiverse because their terms of service says you would then be giving them an royalty-free license to use this. And this is a U.S. patent pending technology. So I want to keep it free for makers, personal use, non-commercial use, and keep it out of corporations' hands without some handshaking going on. So then production preparation. Production preparation is all about kerfs, as I mentioned. I learned that term from machining, and then I saw it again in PuzzleCutLib. So PuzzleCutLib is very good. It incorporates some of the same principles for breaking up a 3D object. So if we go to K_E of 0.9, K_E of 0.9 will it will space out element kerf. So if I adjust to 0.8, you'll see right away there'll be more space between elements. See the gaps increase here. And you might be able to, there we go. So if I go to 9.5, say that I printed it and sampled it and it was too loose, tightened it up by increasing K_E. The hook kerf is the exact principle on hooks with regard to hooks. So with the hooks, you put in a value of 0.8 and that loosens up the hooks. Say your hooks were too tight. And you'll notice that these are percents, so that's 80% of the hook width. So even the element kerf is 95 in this case, 95% of the hook width. It's all relative to the hook width. In other words, it's nice because if you put them both at the same, you'll see that, let me press F6 to render, you'll see that the gap is uniform. So that's really nice. You just match the hook kerfs and the element kerf values, and it will have a uniform gap. So once you've got that where you think you want it, the next step in production preparation is production preparation is production testing. Production testing is so you know that your hooks fit, they don't interfere too much, they don't act like these guys right here. are pretty loose fit. They don't stay together if you just slide them along each other. Whereas on the other end of the spectrum, this one's just right. It doesn't slide apart. You can shake it. And this guy's a little, the kerf values were too high. I pressed this guy together with a vise. And but it does have a nice profile of a sphere. So production testing, you generate sample hooks. That's the easiest part to generate because hooks are much smaller in general than the element itself. So you first print off a pair of hooks by going to your OpenSCAD lib. Again, we'll focus on the executed code here. This section for commenting and uncommenting modules. Comment out what we were doing and uncomment sample hooks. Let's see what happens. Right now we have square hooks, so if I press F6, oh, very tiny there. So we press this magnifying glass to pop into it. Oh, this must not have been a... My apologies. This was not a complete... This is one version behind of element library. So if type of the hook equals 1, so in other words, if it's a rounded hook, then take away from the hook. So this is the change that you'll receive in the GitHub repository. So that fixed that problem. So you won't need to do that part. I apologize. So now it's got the two hooks side by side. You print those. That should take seconds, half of a minute or something, depending on your hook size. I don't know how crazy you'll go with this. But if I was referring to millimeters, it looks like my hook diameter is less than a millimeter. So just do some real quick prints. And you can adjust the sample height here in your parameters. If I didn't believe that they'd fit well over a long distance, then make the sample height taller. So after you got the hooks fitting well, you're very happy with that. Sample hooks are basically all you need to do if you have a ligament-only element. So what is meant by a ligament-only element is the version where efill equals 0. So let's extrude and go back to efill. Change that to 0. If I had these kind of elements with ligament only, you don't worry about element kerfs because elements don't butt up against each other. So hook kerfs are all you need to worry about. Now you're ready to print if you're using a 3D printer. But in the case of a filled element, you'll want to manipulate the element kerfs and print some test elements. So we did sample hooks right there, and now you just go down to sample elements. So if I snap again to the center, it will give you these nice sample elements. You can see how well their faces meet together. You can get that feel of do they chatter or zip together. Here are the elements that I'm using for my stand-up paddleboard that you saw in the overview video. Hopefully you saw that. And they have some good resistance going together. I don't want to punch myself in the face. But that's what I've found really works well. So after you've printed sample elements, printed sample hooks, you're satisfied with how everything lines up, then you're ready for production, basically. In the production, really you're going to make this. So this is my Frisbee. This visualization right here is an intersection of the linear extrude of the elements with the import of the object. This visualization is not important, but it will at least give you, if you're particular about how it looks and maybe want to change the styling of the elements, then you can visualize this way. It takes maybe 2 minutes for something like this to generate on a PC like my Dell 7000 Latitude or something like that. So now that you're ready for production, in the same bit of within this executed code bubbly region, you go down to the third category of production. So you will uncomment production iteration, and you'll see on the website, after testing, repeat, rinse, repeat, go down to production. At the very bottom of your, at the very bottom of the extruded element library we copied from GitHub, there is 3 lines here for production. It's a batch file for Windows users. So if you, it's text for a batch file. So you copy that, Control C, open up Notepad, Control V, paste it in there, and file save as something.bat. That will make it an executable text file, which if you go back to the Extruded Element website, you specify the number of elements, -1 in this value up here. You also will modify that text with the directory where you've stored your STL and your current SCAD file, your current SCAD file. And then you also change your preferred element file prefix. So SUP, stand-up paddleboard, that's what I was calling it when I auto-generated all the elements for my stand-up paddleboard. So I called that sup dash. You can call it what you want. And then lastly, you want to specify the name. I defaulted my library to EELLC, extruded element LLC _lib.scad. So you'll need to make sure all of those are consistent with the way you did things from this. And then you run that batch file. In that directory, it will propagate all of the STL files only where the element intersected with your solid object. For instance, if we go back and look at this frisbee, the grid needed for that frisbee, in other words, the value you'd put in that batch file, n by m, is 9 by 6. So 9 times 6 is 54, -1 is 53. So I would have put the value 53 into there. And even though there are 54 elements, the STL files that you'll find in that directory after running the batch file will only be this many. So maybe 25 elements, 30 elements will actually exist because the rest had no renderable geometry with that intersection command of intersect imported object with extruded elements. So anyways, learn more on Reddit, subreddit extruded element, and share about it. I made a subreddit because I didn't want to cloud up the subreddit 3D printing with very specific method of 3D printing. So please and thank you. Have a wonderful day.